A 32-inch pump is to pump 24,000 gallons per minute of water at 1170 RPM from a reservoir that is open to atmosphere. If the head loss from the reservoir to the inlet of the pump is 6 feet, where should the pump be placed to avoid cavitation? So as we look at this, we can kind of sketch it out. We're looking at some pump here. We have some surface of the fluid. We know that there's 6 feet of head loss total. We can draw a little control volume there and calculate out what's coming into the system and what's coming into the suction side of the pump. We're given the vapor pressure of the water, and we're also given the specific gravity of the water. So where should we place it to avoid cavitation? Well, we're going to go and solve the energy equation. We're going to have to make a couple of assumptions, as always with these problems. First assumption we'll make is a steady flow. Nothing in the problem that says that there's not steady flow. We're going to assume an incompressible flow, constant density. Once again, it states that it's water, and liquids are generally incompressible. Third one we're going to do is assume a constant temperature. There's nothing in the problem that says the temperature is changing, so we're fine. So we drew our little control volume. Let's draw or write out our energy equation. So there's all of the fluid properties coming into the system. Now our control volume here terminates at the pump, so this would also be everything coming into the supply side of the pump, plus the head of the turbine minus the head of the pump, plus the head of friction, so total friction. And as I look through here, let's knock out the low-hanging fruit and make this equation a little bit slower, or excuse me, a little bit smaller. Surface of the large tank, V1 is equal to 0. We're just going to set Z1 equal to 0. We're looking for the height on the suction side. There's no turbine in our system. There's no pump in our system because our control volume terminates before the pump. So that gives us, we've got the pressure coming in, which is atmospheric pressure, the dynamic and static pressure heads coming into the suction side of the pump, the height on the suction side of the pump, plus the head loss total. We do need to put together NPSHA because we want to find the net positive suction head available. So that's plus, we'll add and subtract the vapor pressure head from this, so we can take these terms here and create net positive suction head available. And what does that give us? If we take that and rearrange the equation, we're going to have the height on the suction side is going to be pressure 1 minus the vapor pressure over the gamma of the fluid minus the net positive suction head available minus H total, and that's it. Now we're going to have to calculate out a couple of things. We have H total, that's 6 feet. We know the atmospheric pressure, we know the vapor pressure. We need to calculate out gamma. So we were given specific gravity. Do you remember what specific gravity is? So specific gravity is the density of the fluid over the density of water at 4 degrees C. So in this case, this gives us, if we're dealing in the English system, this would be in slugs per cubic foot for density. But remember, because multiplying by gravity gives us specific weight. So it's also equal to the specific weight of water at 4 degrees C. So if we go and calculate that out, that's going to give us 60.1 pounds per foot cubed. Oh, and let's not skip a step here like I just did. H2 at 4 degrees C for water, if you remember, is just about 62.4. It's actually 62.38, but that's close enough for what we're doing. Okay, now what is atmospheric pressure? 14.7 pounds per inch squared. Subtract that vapor pressure head, 11.52 pounds per inch squared. You can see these units don't work out, so we're going to need to convert this top, 12 inches to 1 foot. We have to remember that they're square, so we have to square our conversion. We're going to subtract from that the net positive suction head available. Well, how much is available? Let's go back up here and look. We're at 24,000 gallons per minute at 1170 RPM. That's 710. Here we go, 1170. We roll that up, and that crosses about here. Probably can say that NPSH available to this, required for this pump is about 37 feet. So we come back over here, minus 37 feet, and then we have our amount of frictional loss of head of 6 feet. So once I go to calculate that out, I'm going to get negative 35.4 feet. Well, I got a negative number. What does that mean? Well, that means I've got to put it, the suction side has to be below the surface of the fluid. So under the situation for this pump not to cavitate, we actually have to put it 35 feet below the surface of the fluid to keep it from cavitating.